So now that you know some information about effective nuclear charge and electron shielding, we're going to jump into these actual properties that we're going to be looking at that are periodic trends. There will be 4 that we're going to cover. This video is going to talk about the first 2. So the first trend that we're going to look at is atomic radius. Atomic radius is literally the size of the atom. How big is the atom? We think of atoms as being circles, even though we're not 100% sure that they are, but it's useful to us when we're creating our models to make elements circles. And so we think of the radius as being the size. So really these questions are going to be things like, which atom is bigger? Now, the size of the atom is determined by the size of the electron cloud. The nucleus of an atom is very, very compacted in the center. It does not contribute to how big the atom actually is. It's that electron cloud that gives the atom its size. And I have here a picture that is a graphic that shows you the sizes of the atoms. So if we look, we can kind of see a trend as we go down a row. Look at hydrogen's tiny, teeny up there. Lithium's bigger. Sodium's a little bit bigger. We keep getting bigger and bigger as we go down. And as we go across a row, we can see that our atoms start bigger and get smaller. And then when we get to the noble gases, it kind of defeats the trend. So remember when we did their electron configurations that the noble gases were the ones that were very stable and they had those full outer energy levels. So noble gases are not included in these trends because they act differently because they're already stable and have that full outer shell. Just so you know that the noble gases kind of don't follow these trends. But we can see with this graphic that it is a pretty nice trend, and that is really what we look at. The further down a column, the larger the atomic radius, and the further across a row, the smaller the atomic radius. Now, that hopefully is easy. That's something you can memorize and compare, but you're also going to have to explain why that is. And an element's position on the periodic table is not an explanation. The element doesn't know where it is on the periodic table. So when we're looking at the why, we have to look at the number of energy levels and or the electron shielding and effective nuclear charge. Okay, so when you're explaining why, that's what you're looking at. Now, so let's talk about this. If we think about moving down a column on the periodic table, the cloud gets larger because energy levels are being added. And those elements in the same column have the same effective nuclear charge. So if we have lithium, it has its nucleus, and it has 2 energy levels. But if we have sodium, it has its nucleus, and it has 3 energy levels. So sodium is going to be a bigger atom than lithium because there is an extra energy level added to the cloud. In the same column, or group, the ZEFF is the same. In column 1, lithium ZEFF would equal the 3 protons lithium has minus its 2 shielding electrons, so it would be a +1. Sodium's ZeFF would be its 11 protons. Whoops. It would be its 11 protons minus its 10 shielding electrons, which would also be a +1. And if you go down all of column 1, you'll see this same trend. However many protons it has minus however many shielding electrons it has would be a +1. So when we're comparing elements in the same column, because they all have the same ZeFF, that's really doesn't have anything to do with the reason that these properties are different, because it's the same ZeFF. So if that was what we depended on, we would expect it all to be the same, but it's not. So now we need another reason, and that is the energy levels. Okay, so that's how those energy levels work as we go down a column. As we go across a row, the effective nuclear charge, now this is where we're going to use effective nuclear charge. That increases. And remember that when the charge is stronger, the electrons are more attracted. So if we have, let's do lithium again. If we have lithium, okay, it has its +3 in its nucleus, and then it has its 2 levels. If we compare that to fluorine, it's going to have +9 in its nucleus, and it's still going to have 2 energy levels. So in the same row, the number of energy levels is the same. But the ZeFF for lithium would be its 3 protons minus its 2 shielding electrons, so it would be a +1. Whereas for fluorine, its ZeFF is going to be 9 protons minus its 2 shielding electrons, so it's going to be a +7. Since +7 is greater than +1, the electrons are more attracted to the nucleus because the nucleus has a bigger charge. So remember those 2 pieces that we have to look at when we're talking about how positives and negatives are attracted to each other. The size of the charges, which when they are in the same row, the size of the charge is different. So the electrons are going to be more attracted to the bigger effective nuclear charge. That's one of the things. The other piece of it is, in the same column, the distance between the electrons and the nucleus changes. So here, with the lithium and the sodium, the electrons, the valence electrons, are closer to the nucleus. So because the electrons are closer to the nucleus, so if they're closer to the nucleus, or the ZeFF is bigger, then there is a stronger attraction. And the stronger the attraction, the more the electron cloud is pulled in to the nucleus. And that's what makes the atoms smaller or bigger. If the valence electrons are more strongly attracted to the nucleus, they get pulled in closer to the nucleus and the atom will be smaller. If the valence electrons are not as attracted to the nucleus, they are spread out more and the atom will be larger. So you will have to explain that, but there's also going to be a part where you just have to identify which one's bigger and which one's smaller. So let's look at some of those. So we're looking at the smallest halogen. So if you want to pause the video, do these, and then I'll come when you turn it back on, I will reveal the answers and see if you got them right. Okay, so let's look at these answers. If we look at what is the smallest halogen. So the halogens, remember, are column 17. So they're in a column. We know that as we go down a column, layers get added to our cloud. So the one with the least amount of energy levels is going to be the smallest, so that would be fluorine, is our smallest halogen. The largest actinide, remember the actinides come after actinium. As we go across a row on the periodic table, which the actinides are, the effective nuclear charge increases. So the one with the smallest effective nuclear charge is going to be the largest, so that would be thorium. The largest transition metal is going to be actinium. Remember, actinium is down in that corner of the transition metals. So it's going to have the most energy levels and the smallest effective nuclear charge in that block. The largest atom on the whole periodic table would be francium. And then comparing nitrogen, silicon, and gallium, they're all in a diagonal. And we know that atomic radius decreases across and increases down. So the one closest to the upper right-hand corner is going to be the smallest. All right. So we'll do more practice with that tomorrow in class. But I also want to talk about another very similar trend that kind of goes hand in hand with this one, and that is ionic radius. So ionic radius is the size of an ion. Now, the general trend is the same when we're comparing ions to each other, but remember that we have two different types of ions. We've got we've got anions and we've got cations. Anions and cations. Anions are going to be bigger than the atom from which they are made. That should make sense because they gain electrons, and that's going to make them bigger. When they add electrons, there's more electron repulsions. That's going to cause the cloud to spread out. Cations lose electrons, and so that means that they're smaller than the atom from which they are made. Again, that should make sense because if you lose something, you get smaller. If you lose money out of your bank account, you get a smaller bank account. These are still determined by the size of the electron cloud, but now we're comparing these ions. Remember, these are atoms that have lost or gained electrons. So if we look at our picture, what I was talking about before, the gray on this picture is the neutral atom and the colored is the ion. So we've got lithium. When it loses an electron to become lithium plus 1, it gets smaller. We've got beryllium. When it loses 2 electrons to become beryllium plus 2, it gets smaller. On the non-metal side, we've got oxygen atom. When it gains electrons to become oxygen minus 2, it gets bigger. When chlorine gains an electron to become chlorine minus 1, it gets bigger. Okay, so that's one of the trends. The other thing is comparing the ions to each other. So we can see like just this pink part. Lithium to beryllium to boron gets smaller and smaller and smaller. The anions also get smaller as we go across. So we have to compare cations to other cations and anions to other anions. We can't compare cations to anions. It's like apples and oranges. We can compare a neutral atom to a charged one too. So if we look at the trend for this, it's the same. as the trend for atomic radius. The further down a column, the larger the ionic radius. Across a row, the smaller the ionic radius. And in terms of the why, the explanation, it's the same. If we move down a column, the electron cloud gets larger because energy levels are being added and valence electrons are further from the nucleus. So those valence electrons get further from the nucleus, which means they're less attracted, which means the cloud spreads out. As we move across a row, the effective nuclear charge increases and causes the electron cloud to be closer to the nucleus. So stronger charge equals greater attraction. So it's the same reasons for atomic radius. Okay, so let's do some practice with that before we get to class. Again, pause the video, see if you can do these, and then when you start it, I will go over answers. Okay, so comparing the fluorine to the fluorine ion. So this is comparing a neutral atom to its ion. Anions have gained electrons. When they gain electrons, they become bigger. So F-1 is bigger. Now we're looking at smaller, Mg to Mg plus 2. When elements lose electrons, they become smaller. So Mg plus 2 is smaller than neutral magnesium atoms. Okay, now we're comparing ions to each other. We've got sodium, potassium, and rubidium. They're all alkali metals. They're all in the same column. They want the largest one. We know that down a column, my ionic radius increases because I'm adding energy levels to my clouds. So rubidium is the largest of those three. In number 4, we're comparing anions to each other. We've got N-3, O-2, and F-1. The smallest is going to be F-1. We know that the ionic radius decreases as we go across because our effective nuclear charge increases, and that pulls the electrons closer. And then lastly, the smallest of Al plus 3, Ga plus 3, or In plus 3 would be Al plus 3. Because these are all in the same group, and we know that the smallest one is going to have the fewest energy levels, which is Al plus 3.